to our YouTube channel. Today we'll be continuing our series on the metabolism of carbohydrates, and we'll be taking an exciting topic today: digestion and absorption of carbohydrates. Now, of course, like we said last time, the series is sweet one, but for metabolism, everything in metabolism starts with digestion and absorption. Yes, I know I'm to get energy. Yes, I know it's headed somewhere, but ultimately everything begins from digestion and absorption. Now, as a way of definition, what is digestion? What is digestion? Digestion is the breakdown of complex food materials into simpler absorbable forms. So I have something complex being broken down into smaller tiny particles, and this occurs in the GI tract. So at different levels of the GI tract, we could have different levels of digestion, but ultimately digestion is what I said, which is breakdown of large into simpler forms. Now, absorption, on the other hand, is the transport of these digested food substances from the tract to the blood. So it was broken down within the tract. After I'm done with the breaking down, it is not useful to the body if it stays within the tract. It has to be carried to cells. But before it gets there, the means by which to transport things from one place to another is the blood. So of course I have to carry them from the tract to the blood, and that is what we call absorption. So we have our tract here on the wall called the GI tract. Oh, every tract should have a lumen, and then you should see the walls. Now, after I've had my big chunk of carbohydrate, it's being broken down into smaller forms, a process called digestion. Now, after being broken down, it's now carried inside the blood. And like we said earlier, so this is our blood, and this process here is called absorption. Now, we go ahead. So this is digestion, this is absorption. Now, before we jump at it, we jump into the details of digestion, it is very important we know what kind of food. We mentioned these foods are complex, they are large, but what kind of carbohydrate, what form of carbohydrate do I have in my diet? What form of carbohydrate do you have in your food, the food we take every day? Now, we have about 5 forms of carbohydrates. So we call them dietary forms of carbohydrates. We have about 5 forms. Of course, 4 are more common. So I'll dwell on the 4, but I'll mention the 5th one. Now we have starch. Almost every single food we take, as far as it's plant derived, every single food that we know that has plant derives from plant derived, gari, whatsoever you can think about, that is starch, and it is carbohydrate. So any form of carbohydrate I get from plants will be starchy. Of course, apart from sugar cane, which I'll mention later. Then also we have glycogen. Now, glycogen in this case is animal, when I derive it from the animals. So now, for example, now the case is when we take food is not entirely, unlike the notion we used to have. For example, if a question was thrown and then you are asked, what class of food is bread? You would jump at the idea, oh, it should be carbohydrate. What class of food is beans? You should think proteins. What class of food is meat? You should think proteins. But nutritional biochemistry helps us to know that it's not that way. That food is not entirely, no food entirely belongs to a particular class. Most times, when I pick any food we eat, any particular food, it is balanced on its own. That means it could have some of carbohydrate, a bit of protein, but it could be majorly carbohydrate. For example, bread is majorly carbohydrate, around 55% based on how it is prepared. Then you go to proteins, when you go to beans is protein, but it also has some amount of starch. That's why when you parboil, you should see it. We have some amount of starch in beans. So you realize, even when we take meat, for example, there's some amount of starch. I'm saying starch, there's some amount of carbohydrates in beans. But it is worthy of note, meat. And it's worthy of note that this particular carbohydrate we have in meat is glycogen. Why? The storage form of carbohydrates in animals is glycogen. So that means if I should eat an animal after a while, I should eat an animal as in form of meat, and then I'm taking the carbohydrate that was stored, it has to be in glycogen form. I believe we are following me. Now I go ahead. Others we could have is dextrins, not so commonly talked about by the books. And then we have, they make mention of sucrose and lactose. Sucrose is commonly found in sugar cane, whereas lactose is commonly found in milk. So I run over it again. What are the forms of these complex carbohydrates we can have in food? What are the forms of the complex carbohydrate we can have in food? Yes, we can have the starch, which is plant food. If I'm eating a plant food that has carbohydrates, then we're speaking starch. Then if I'm eating an animal food like meat here, when I keep mentioning meat, it could be liver. Most time people eat, and you eat a liver of a particular animal. Yes, most likely having glycogen there. Then dextrins, we have sucrose majorly in sugar cane, and then lactose majorly in milk. So that's that. Now we come into the proper of digestion. Now digestion, which is the breakdown of those complex to smaller, are achieved by series of enzymes which belong to a particular class of enzymes called hydrolysis. Now, when the classification of enzyme was discussed, or when we talk about enzymes in proper, we'll dwell on their classifications. And the class 3 enzymes are called hydrolysis, of which a key example is our digestive enzymes. So digestion is achieved by set of proteins we call enzymes. Now, for carbohydrate digestion, we have different kinds of enzymes, and these enzymes are found in different locations. And in each of these locations, there's a particular juice or a particular fluid that are found within. So, for example, along the GI tract has different parts because we have the mouth. Everything begins from the mouth. Then it lands in the pharynx. From pharynx, so we have the mouth. Of course, not just the nose and the mouth opens into the pharynx. The nasal cavity and the mouth opens into the pharynx. Now, when we come down from the pharynx, we now have the larynx in front that will turn out to be trachea, and behind we have our esophagus. So as I go down, I would see, as I keep continuing from my mouth, we now keep moving and you land in the esophagus. So let me do that here so I can see clearly. So I have the nasal cavity, the buccal cavity, all opening into my pharynx. From pharynx, you have esophagus behind. And then in front, we have our larynx. Now the esophagus continues. From there, we have the stomach. And then from the stomach, we can now think the duodenum, of course, other part of the small intestine. And then we have our large intestines. And then everything lands with the rectum, and you go to the anus. So, of course, the GIT begins from the mouth goes down to the anus. Now, at different points along this tract, there are points of concern, like the stomach clearly shown here, and the small intestine shown here. The first part of the small intestine is called duodenum. Now, when we go through it, we start off with the first part of concern. In the mouth, there is a particular juice in the mouth, and that juice is called saliva. Yeah, of course, when we mention juice, we're not talking chi exotic. The juice in this case is a fluid found in the mouth, and the fluid in the mouth, we touch it, we feel it every single day, is saliva. And then it has its own enzyme for digestion of carbohydrates, and that enzyme is called salivary alpha amylase. It's otherwise called ptyalin. So salivary amylase or ptyalin. Now, when I keep going down, I get to the stomach. The stomach has a juice called gastric juice, but this juice has no function with carbohydrate digestion. Why? It lacks enzymes for digestion of carbohydrates. Rather, it is concerned with protein digestion, which is a discussion for another day. Now, I get to the duodenum within the small intestine. We also have an enzyme for it, but the juice here, pancreatic juice, we go to the main other part of small intestine, and we also have a juice called intestinal juice. So now let's dive right in. Now, so we begin with the mouth. Within the mouth, like we said, the enzyme of concern in the mouth is the juice in the mouth is saliva, and the enzyme I have here within the mouth is salivary alpha amylase. The alpha term here is because it breaks down alpha 1,4, like the bond it breaks is alpha 1,4 glycosidic bond. So the idea of alpha is because of the type of bond it breaks. So we have salivary amylase in the mouth. Now, this salivary amylase is also called ptyalin. Now, of course, I wouldn't stop at the enzyme, because not only the enzyme that's important in the mouth. In the mouth, we masticate, that we chew. And while you're chewing, you're also breaking down that complex food substance. At least you are trying to break it down to smaller forms. So when your food mixes in our mouth while we are chewing, it is exposed to this enzyme we call alpha amylase. But it is very important you take note of the fact that when we're talking about the dietary forms of carbohydrates, we establish that we have starch, glycogen, then we have dextrins, we have sucrose, and then we have lactose. Of the five, the first three, the starch, the glycogen, and the dextrins, are all starch, glycogen, and dextrins. All of them are polysaccharides, whereas our sucrose and lactose are disaccharides. Now, the stuff is in the mouth. The only ones that can be digested within the mouth are the polysaccharides. So that means my sucrose has no business in the mouth. My lactose has no business in the mouth. So if I should ingest milk, or I should take in sugar cane, there's nothing that has to do with mouth. Like there's no form of digestion of the lactose within them. I believe you're following me. So there's no form of digestion within the mouth that has to do with lactose. So here, the alpha amylase we are talking about here has an average pH, an optimum pH of 6.7, an optimum pH of 6.7, and a range of 6.6 to 6.8. So along this range, 6.6 to 6.8, it is favorable for him, but the optimum pH is 6.7. Now it requires chloride ion for its activation. Salivary alpha amylase requires chloride ion for its activation, and its action, it's simple. It works on glycogen, it acts on starch, and then it acts on dextrins. Remember what we said? Please, it is important to note, you can take it as a footnote, that digestion of disaccharides begin or happen in the small intestine. They have no business in the mouth. Within the mouth, who are we digesting? Just the glycogen, the starch, and the dextrins. And this action is by our alpha amylase. And our product here could either be maltose, maltotriose. Maltose is just 2 glucose. Maltotriose is 3 glucose, has 3 glucose subunits. And then we could also have alpha dextrins. That's if we're working on our dextrins here, we'll now have alpha dextrins. It is important to note from what you heard me say, now glycogen, starch, and dextrins are all homopolysaccharides. That means they have only one kind of monosaccharide unit, and that is glucose. So if I should break down starch, the only thing I can get from starch is glucose. The only thing I can get from starch is glucose. Likewise, same thing happens with glycogen and dextrins. So when they are broken down by the action of alpha amylase, what we end up with is our maltose, maltotriose, and alpha dextrins. It is important you note that this particular guy we call salivary alpha amylase or ptyalin works under a favorable pH of 6.7, and then it requires chloride for its activation. It requires chloride for its activation. And as earlier said, it breaks the alpha, the bond. It breaks the bond. And these bonds must be within. So you realize there's no glucose formed here because it breaks bond within the long chain. It's not at the ends. So I go forward. Now, by the time we are done with the mouth, our next target is the stomach. And in the stomach, like we said, the juice we have in the stomach is called gastric juice. But sadly, it has no enzymes for digestion of carbohydrate. It has no enzyme for digestion of carbohydrates. Now, we now go to the next guys, which are the small intestine. Within the small intestine, we have 2 juices of concern. Now, so within the small intestine, we don't just have one kind of fluid or one kind of juice. We have 2. One is found within the duodenum, and it's called pancreatic juice. Now, aside from having the main GI tract, which is a muscular tube, now the GIT is supported by some other organs we call accessory structures or some accessory organs of the GI tract. And one of these organs is the liver. You've seen what the liver does. We mentioned it in our first video, how the liver helps in metabolism. Aside from the liver, we could also have something like the pancreas, and pancreas is important in production of pancreatic juice. Aside from that, we could have the gallbladder for storage of bile. So now here, once the pancreas is done producing this juice we call pancreatic juice, it is poured into, or it is drained into the duodenum or the small intestine, and it's the first part of the small intestine called duodenum. So that means within the small intestine, I have two types of juice. Pancreatic juice. For most books, they just mention this as duodenum. So under duodenum, we have pancreatic juice. And then the particular enzyme in pancreatic juice that is important in digestion of carbohydrates is pancreatic alpha amylase. Now, why is pancreatic alpha amylase important to us? You see, the name is alpha amylase, and that was a similar name to the guy we had in saliva, which was salivary alpha amylase. Now, we are told that you realize that some people that are taking food without chewing the food, some people eat food without chewing, some people swallow food. So when someone swallows food, the time frame you have the food in your mouth is short, and so there is no adequate time for saliva to mix and for this enzyme to work. So there is a need for us to have someone similar to him and even more powerful than him, and that is pancreatic alpha amylase. The action of pancreatic alpha amylase is similar to that of salivary alpha amylase. It has a pH, an optimum pH of 7.1, and then it also requires chloride for its activation, and its action is the same as that of salivary alpha amylase. Why is this important to us? So you realize that in saliva, I had someone that could break down glycogen, starch, and dextrins, my polysaccharides, into this. And then I come to small intestine and still have them here. It is even believed that if for any reason we were to bypass eating in the mouth, maybe you're taking food that's not to the mouth, maybe directly to the stomach or directly to the small intestine, on getting there, digestion will still go unchecked. It will still go on normal as if there is no problem with salivary alpha amylase. But in a normal person that is chewing well, of course, some of the food will be acted upon here. But when they get to the small intestine, the pancreatic alpha amylase will still act on them. Now, why do you think it's able to do its action? Now, as food is passing through the small intestine, the motility in the small intestine is actually very slow. So the food is going down slowly. So there's enough time for mixing with the pancreatic juice. And as you're mixing with the juice, of course, you are exposing the carbohydrates to the enzyme called alpha amylase, so it can do the action. So by the time I'm done taking a carbohydrate food, maybe not even most, some of them could be digested here. Even when they're digested here, when they get to the small intestine, anyone that was not digested will be acted upon by alpha amylase. Some people that swallow food without chewing might not have enough time for this to happen, so they will skip and then get here. But by all means, polysaccharides will be digested, and we'll have maltose, maltotriose, and then alpha dextrins. Then we go to the other part of the small intestine. And here we now have our intestinal juice. Now, another name for intestinal juice is sulcus entericus. That should be a Latin word, sulcus entericus. Anytime we hear enteric most times talk about the GIT, but if you have to be more specific, it will be talking about the small intestine or the intestine as a whole. So when we see this sulcus entericus or intestinal juice, so apart from the pancreas producing juice, a particular juice, and sending it into the GI tract, the small intestine, the wall of the small intestine itself can produce this juice. And this juice is called intestinal juice or sulcus entericus. And the enzymes we have here that are of concern or that are concerned with carbohydrate digestion include our maltase, our lactase, and our sucrase. So like you can see from the name, maltase, an enzyme that will act on maltose. Lactase, an enzyme that will act on, remember we mentioned that we could that digestion of disaccharide begin or can only happen in the small intestine. So lactase will act on lactose, sucrase will act on sucrose, and we also have isomaltase. So when we look at our enzymes, maltase can act on maltose, it can also act on our maltotriose. And what is its function? Just to break them down. And then we can have our isomaltase acting on our alpha dextrins and maltotriose in this case. So you realize maltase, lactase will act on lactose, sucrase, and then isomaltase, maltotriose, and even alpha dextrins. But now their action, no matter who they are acting on, if it is maltose, that means it will be acting on maltose, and the end product will be glucose. Now, if it is sucrase, it will be acting on sucrose, and our end product will be glucose and fructose. If it is lactase, it will be acting on lactose, and our end product will be glucose and galactose. So we have glucose, fructose gotten from sucrose, under the influence of sucrase. We have from lactose, we have glucose, galactose, and then from maltose, we have 2 glucose. That is glucose plus another glucose. Now, if there was a maltotriose, that's 3. To break them down into glucose, glucose, glucose. The extremes are broken down to form glucose. So in the end, what have we learned on digestion? In digestion breaking down of complex to simpler forms that can be absorbed. Now, it starts in the mouth. Digestion of carbohydrates starts in the mouth, where an enzyme called salivary alpha amylase acts on the food substance and then breaks it down. Salivary alpha amylase breaks it down, but the particular carbohydrate it acts on is glycogen, starch, and dextrins, and it gives us maltose, maltotriose, and then alpha dextrins. Now, this enzyme requires chloride. It has an optimum pH. We get to, by the time food goes down to the stomach, here there is no digestion, and the action of salivary amylase is paused because the pH in the stomach is more acidic and it is not favorable for him. Now we get to the small intestine. On encountering the duodenum, there's a juice in the duodenum called the pancreas, so a pancreatic juice produced by the pancreas, and this juice contains alpha amylase, and it acts doing the same action that salivary amylase would have done. And I established that this is important because for food that could not be digested in the mouth, maybe due to improper chewing, or maybe the short duration of food in the mouth, or even because the food might be much, so there's no time for the guy for salivary amylase to work, so it will now be acted upon by pancreatic alpha amylase, and it's still the same work. Now, by the time we get to the other part of small intestine, even within the duodenum, that's the entire length of small intestine, the wall of the small intestine produces a juice called intestinal juice, and within this juice we have 3 enzymes: four: maltase, lactase, sucrase, and isomaltase, all concerned with carbohydrate metabolism. Now, when we go to other metabolisms, we mention how it's important. We have other people that could help in other metabolism, but this is specific for carbohydrates. Now, maltose for maltose, maltase for maltose, lactase for lactose, sucrase for sucrose, and isomaltase for maltotriose and our alpha dextrin. So that brings us to the end of digestion. So stay tuned as we continue our series on absorption.